Okay, so we are back again. So in the previous example, we have seen that the delta 1 and delta 2, the state variables for the 3 bus system, since knowing them allows all other quantities to be calculated, right. So in general, the state variables for a power system consist of the bus voltage magnitude at all buses and the phase angle at all but one bus, that is slack bus, right. Note that we could use real and imaginary components of bus voltage if desired. So, all these things we have seen. If we, but just starting from the end of the previous lecture, if we can use measurements to estimate the states, that is voltage magnitude and phase angle in this case of the power system, then we can go on to calculate any power flows, generation, loads and so forth, right, that we desire. The transformer taps and phase angle regulator positions should also be considered as state variables, since they must be known in order to calculate the flows through the transformers and regulators, right. So, that is what we have seen. Now, just hold on, let me increase the size. So, now to return to the 3 bus DC power flow model, we have 3 meters providing us with a set of redundant readings with which to estimate the 2 states, that is delta 1 and delta 2. There are 2 states, but we had 3 measurements, right. So, readings are redundant since only 2 readings are necessary to calculate delta 1 and delta 2. The other reading is always extra. However, the extra reading does carry useful information and ought not to be discarded summarily, right. So, that is why if it is so, then we will go for a new concept, right, that how we can accommodate all these things. So, for state estimation, that we will do static state estimation, but we will see 3 types of cases we will see. Mainly one is that when number of state variables are greater than your number of measurement, that is ns greater than nm. Another case, number of state variable is equal to number of measurement, that is ns is equal to nm. Another is number of state variables where ns less than nm, that is number of state variables less than number of measurements, right. So, maximum likelihood weighted least square estimation, likelihood means probability, right. So, statistical estimation refers to a procedure which one uses samples to calculate the value of one or more unknown parameters in a system. Since the samples, that is measurements, right, I have underlined this one, are inexact, that is not true value, not correct value, right. The estimate obtained for the unknown parameter is also inexact, but we have to see that how close it is to the true values, right. This actually leads to the problem of how to formulate a best estimate of the unknown parameters given the available measurement, right. The following 3 are perhaps the most commonly statistical criteria encountered. Number 1 is the maximum likelihood criteria. Here actually, that is maximum likelihood means it is probability, that you have maximized the probability, right, where the objective is that to maximize the probability that the estimate of the state variable x cap, right, is the true value of the state variable vector x, that is maximize p x cap is equal to x, you have to maximize the probability. This is maximum likelihood criterion, right. Next one is that the weighted least square criterion. Here, where the objective is to minimize the sum of the squares of the weighted deviations of the estimated measurements, that is z cap from the actual measurement, that is z, right. Sorry. So, this is weighted least square criterion. Third one is the minimum variance criteria, right. In this case, it is actually objective, right, by it is written object, it is objective, where the objective is to minimize the expected value of the sum of the squares of the deviation of the estimated components of the state variable vector from the corresponding components of a 2 state variable vector, right. So, these are the actually your what you call it is variable and it is actually true, right, 2 state variable vector. It is little bit cut, but just I am telling this one, this is actually true value, right. So, that is actually these 3 different criteria you have, and we have to follow certain things, right, the certain mathematical procedure. Now, when normally distributed, that is unbiased meter error distributions are assumed that each of these approaches results in identical estimators, right. We will utilize the maximum likelihood approach because the method introduces the measurement error weighting matrix R. Sometimes what I will do, when I am writing it is actually R, it is R matrix, instead of that some later we will use R only. So, understandable, right, just put in bracket that shows that your matrix, right. So, it is in a straightforward manner. So, we will utilize the maximum likelihood approach because the method introduces the measurement error weighting matrix R, right, in a straightforward manner. So, sometimes we will sometimes I will simply write R, right. So, but here I have made it in bracket R to show that it is a matrix. So, the maximum likelihood procedure asks the following questions, that is, what is the probability, in bracket I have written, or likelihood that I will get the measurement I have obtained, right. So, this is that criteria, the maximum your likelihood procedure, right. So, this probability actually depends on the random error in the measuring device, that is transducer, as well as the unknown parameters to be estimated. Therefore, a reasonable procedure would be one that simply choose the estimate as the value of maximizes this that maximizes the probability, right. The maximum likelihood estimator assumes that we know the probability density function, that is called PDF, right, of the random errors in the measurement. Now, first let us introduce the concept of random measurement error. The measurement errors are assumed to be in error. We are assuming that every measurement has some error. For example, when you are doing your experiment in the laboratory, you have ammeter, voltmeter, wattmeter and other type of meters. When you take the reading, you will see that as soon as you connect and try to take the reading, you will find the pointer actually oscillating around some point. When that pointer is settling to some point, you are taking the reading. Basically, you are taking the mean reading, right, because it is, or true reading is there, but both sides you will find the pointer is oscillating. So, ultimately when it is settled down, you are taking the reading, basically that is mean reading, right. And in the ammeter or voltmeter, just check, it will be written somewhere instrument that accuracy. Suppose if it is written that accuracy is plus minus 3%, right, that is if it is written like this. So, that is actually 3 sigma, right, is equal to plus minus 3%, the standard deviation, right. So, that the value obtained from the measurement device is close to the true value of the parameter being measured, but differs by an unknown error, because we are measuring, but measurement is not your exact, right, it is inexact. So, some error will be there. So, now let us make it like this, that you assume that Z measure, right, let Z measure, that is your this one, be the value of a measurement or as received from a measurement device. It may be volt, it may be current, ampere, it may be megawatt, it may be megavar, right, like this. So, and let Z true, this is Z true, be the true value of the quantity being measured. This is the measured value and this is the true value, right. Now, let zeta be the random measurement error, right. Therefore, we can write that Z measured is equal to Z true plus zeta. This is equation 1. So, this is our true value, but we are assuming that zeta be the random measurement error. So, Z measure actually Z true plus zeta, right. So, that way we will define that, and now the random number zeta actually serves to the model uncertainty in the measurement, right. So, this is actually a random number, it serves to the model the uncertainty in the measurements. If the measurement error is unbiased, right, the probability density function of zeta is usually chosen as a normal distribution with 0 mean. So, that means if the measurement error is unbiased, the probability density function of zeta is usually chosen as normal distribution with 0 mean, I mean its mean is 0. Therefore, if it happens, so note that the other measurement probability density functions will also work in the maximum likelihood method as well. So, if the mean value of, I mean, we are writing z measure in the previous equation, equation 1, z true plus zeta, right. If the mean value of the your what you call your random number, that zeta is 0, therefore, mean value of z measure will be is equal to the mean value of z, I mean this thing z true, right. So, that is why the probability density function of zeta can be written as it is a normal distribution your probability expression, that is PDA, probability density function zeta is equal to 1 upon sigma root over 2 pi into e to the power minus your zeta square upon 2 sigma square. This is equation 2. This you know, this expression from your mathematics probability chapter, you know this expression, this is standard expression for normal distribution, where sigma is equal to, you know, the standard deviation of the random number, and sigma square is the variance of the random number, right. Now, PDF zeta actually describes the behavior of zeta, right. So, this is a we define this one as a probability density function zeta is equal to this, it is a normal distribution. Sorry. So, now we will go to the next page, just hold on. So, the plot, just hold on. So, the plot of probability density function, that is PDF zeta versus zeta is given, this is sigma, this is 2 sigma, this is 3 sigma, and it is actually your what we call the normal distribution, the PDF zeta versus zeta curve, right. And note that sigma, the standard deviation, provides a way to model the seriousness of the random measurement error, right. So, if sigma is large, the measurement is relatively inaccurate, that is a poor quality measurement device, because your standard deviation is large, that means the measurement device is not giving you the best answer, right, best measurement. So, it is a poor quality measurement device, whereas a small value of sigma, when sigma is very low, that is standard deviation is very low, denotes a small error spread, that is a higher quality of measurement, higher quality measurement device, right. Now, the normal distribution actually is commonly used for modeling measurement error, since it is the distribution that will result when many factors contribute to the overall error, right. So, for example, say you consider a maximum likelihood concept, that how things are. For example, you consider a simple DC circuit, right. It has a voltmeter, it is given like this, x2 is actually the volt, and there is an ammeter also, and it is measuring the current, we get Z1 measurement, and R1 is the resistance of the circuit, right. So, the principles of maximum likelihood estimation is illustrated by using a simple DC circuit example, and as shown in figure 6, right. So, this is the voltage, it is the true value, we have to estimate this true value of the voltage, and we have taken a simple circuit first. So, it is a voltage source, and an ammeter is there, one resistance is there in R, that is R1, right, and this is Z1 measure. Actually, if this is Z1 measure means it is the ammeter, ampere. So, Z1 measure means it will be x2 upon x upon R1 in general, right, because x is the volt and Z is the current, ampere, right. So, now in this example, we wish to estimate the value of the voltage source x2 using an ammeter with an error having a known standard deviation. We know the ammeter, and we know the standard known standard deviation, right. Now, ammeter gives a reading of Z1 measure, this is actually giving a reading, that is Z1 measure, right. So, which is equal to the sum of the Z1 true, that is the true current flowing in figure 6, this is the true current flowing in this figure 6, right, and zeta 1 the error present in the ammeter. This expression we have seen that Z measure is equal to Z true plus zeta. So, here it will be Z1 measure will be is equal to Z1 true plus zeta 1. So, here now we can write that Z1 measure is equal to Z1 true plus zeta 1, this is equation 3. Therefore, zeta 1 zeta 1 is equal to your Z1 measure minus Z1 true, right. So, because that zeta 1 expression we will use, since the mean value of zeta 1 is 0, I told you, we then know that mean value of Z1 measure is equal to zeta 1 true, right, because this zeta 1 mean value is 0, So, mean value of Z1 measure is equal to Z1 true, right. This actually allow us to write a probability density function for Z1 measure as. So, in this case we can write then PDF Z1 measure is equal to 1 upon sigma 1, the standard deviation is sigma 1 root 2 pi, right, into e to the power, actually it was minus your zeta 1 square upon 2 sigma 1 square, but zeta 1 is equal to Z1 measure minus Z1 true. So, that is why it is minus Z1 measure minus Z1 true whole square upon 2 sigma 1 square. This is equation 4. This is the probability density function for Z1 measure, right, where sigma 1 is equal to standard deviation for the random error, that is zeta 1. If we assume that the value of the resistance R1 in figure 6 is known, then we can write, right, we are assuming that in the figure 6 the resistance of the DC circuit R1 is known, then we can write that your this term, that Z1 to Z true, that is your Z true is equal to x upon R, because Z is the your ammeter reading, say it is ampere, and x is the volt. So, volt by your resistance R, so ampere. So, Z actually Z true is actually x upon R1, this term is replaced by x upon R1. That means, my PDF Z1 measure is equal to 1 upon sigma 1 root over 2 pi e to the power minus bracket Z1 measure minus x upon R1 whole square upon 2 sigma 1 square. This is equation 5, right. Now, coming back to our definition of a maximum likelihood estimator, we now wish to find an estimate of x called x is equal to x est, that is x estimator, right, that maximizes the probability that that the observed measurement Z1 measure would occur, right. So, this is for just a simple circuit we have taken, and this is the probability density function for Z1 measure. Since we have the probability density function of Z1 measure, we can write like this: the probability of Z1 measure is equal to, it is actually Z1 measure to Z1 measure plus d Z1 measure, right, that is integration, this is limit, then PDF Z1 measure into d Z1 measure, right. As d Z1 measure actually tends to 0, you can write PDF Z1 measure into d Z1 measure, right, because d Z1 measure is a very small thickness, very small one. I suggest you go to the graph and just find out how things are happening, but from your probability studies you have studied this, right. So, since we have the probability density function like this, then this one actually can be written as PDF Z1 measure into d Z1 measure. This is equation 6, right. So, next, the maximum likelihood procedure then requires that we maximize the value of probability Z1 measure. We have to actually maximize this one, that probability of Z1 measure, we have to maximize this one, right. So, nothing but you have to maximize this one, PDF Z1 measure, right. So, therefore, which is function of x. So, the maximum likelihood procedure then requires that we maximize the value of probability of Z1 measure, which is actually a function of x, that is maximize probability of Z1 measure, and it is function of x is equal to maximize your PDF Z1 measure into d Z1 measure, right, and that is your equation 7. Now, how to maximize this? Things are very simple. One convenient transformation that can be used at this point is to maximize the natural logarithm of PDF Z1 measure. Since maximize the your ln, that is natural logarithm of PDF Z1 measure, will also maximize PDF of your Z1 your what you call measure, right. So, when we try to maximize PDF of Z1 measure, if you take its natural logarithm, it will be the same thing. So, if it is so, then we wish to maximize, wish to find out maximize the natural logarithm of PDF Z1 measure, right, for which you can find out the true value. So, if you do so, you take natural log of this equation, this equation you take the natural log, right, then what will happen? That it will be minus ln sigma 1 root 2 pi, but then minus your what you call 2 into ln Z1 measure minus x upon R1 divided by your what you call divided by 2 sigma 1 square, right. So, here also we have written that one, that your maximize, that means maximizing PDF function Z1 means same thing, that maximizing natural log of PDF of Z1 measure. So, this will be maximized minus ln sigma 1 root 2 pi, and this is minus your Z1 measure minus x upon R1 whole square upon 2 sigma 1 square, because we have taken the natural log, right. Now, since the first term is constant, because this is a constant, if first term is a constant, right, if the first term is a constant, so generally maximize means we have to take ddx, but anyway of 0, ddx of that term is first term is your what you call it is a constant, and second term a minus sign is there before this term, a minus sign is there. That means maximize this term means minimization of this term actually will maximize this term, because first term is a constant, right, and a minus sign is there before that. Therefore, we can maximize the function in brackets by minimizing the second term, since it has a negative coefficient. This is negative, right. Therefore, just hold on. That is your maximize your, just hold on, let me increase its size. That is your maximize x minus ln sigma 1 root 2 pi minus Z1 measure minus x upon R1 your what you call whole square upon 2 sigma 1 square. It is simply actually minimize x, that is Z1 measure minus x upon R1 whole square divided by 2 sigma 1 square. This is equation 8. So, minimize x means you will take ddx of this one is equal to 0, right. That means the value of x that that minimizes the right hand term is found by simply taking the first derivative and setting the result to 0. That means ddx of this one is equal to 2 will come, but 0 both side the right hand side is 0. So, in general it will come minus Z1 measure minus x upon R1, that is in bracket, divided by R1 sigma 1 square is equal to 0. This is equation 9. Solving this at if you make that x is equal to x est, right, estimated value. Therefore, x is equal to x estimated value is simply R1 into Z1 measure. This equation I have marked it as 9a. So, for a simple voltmeter and ammeter, you are getting the same result like V is equal to IR, because Z1 measure is nothing but the I, and this is the R1, and this is x is nothing but the V, right. So, here actually only 1 meter is there, and you are just trying to find out the true value of the voltage. So, it is quite straightforward, right, but simply it is V is equal to IR. So, this is a simple one. Now, suppose now we have say 2 ammeters in parallel, and one resistance is R1 here, one resistance is R2 here. Current measured by ammeter 1 is Z1 measure, and current measured by your ammeter 2 it is your Z2 measure, right. And this is the true value of the voltage, that is V. We have to estimate the true value, and this ammeter has standard deviation sigma 1, and this ammeter has standard deviation sigma 2, right. And that error for this ammeter it is zeta 1, and for this one it is zeta 2. So, it is a simple parallel circuit. 2 resistors are connected in parallel, right, and across that a voltage source is there. That means all 3 quantities are in parallel, and these 2 ammeters measuring Z1 measure and Z2 measure the current flowing to the ammeter, right. So, it is a simple DC circuit. Now, assume that both R1 and R2 are known as before, each meter reading as the sum of the true value and a random error, right. Now, we know from the same procedure Z1 measure will be equal to Z1 true plus zeta 1, and Z2 measure will be Z2 true plus zeta 2. So, these 2 equations combined we mark as a equation 10, right, where the errors will be represented as independent zero mean normally distributed random variables with probability density function. So, it is I mean they are not your what you call influencing, one meter reading is not influencing the other meter reading, that completely independent, right. So, therefore, PDF zeta 1 we can write 1 upon sigma 1 root over 2 pi x e to the power minus sigma 1 square upon 2 sigma 1 square zeta 1 square upon 2 sigma 1 square. So, zeta 1 is Z1 measured minus your Z1 true value. Similarly, PDF zeta 2 is equal to 1 upon sigma 2 root over 2 pi e to the power minus zeta 2 square upon 2 sigma 2 square. So, zeta 2 is nothing but z measure 2 minus your what you call that your z true value divided by your that will zeta 2 and divided by 2 sigma 2 square, right. This is these two equation combined is equation 11, right. And as before, we can write the probability density function of z1 measure and z2 measure. So, in this case, if we do so, PDF z1 measure is equal to 1 upon sigma 1 root 2 pi e to the power minus of z1 measure minus x upon r1 whole square divided by 2 sigma 1 square. It is same as before, that your z1 measure minus z2 and z2 is equal to, it is a parallel circuit. So, z1 true will be x upon r1. Similarly, it is a parallel circuit, the z2 will be x upon r2, right. That is why this PDF z1 measure is equal to 1 upon sigma 1 root over 2 pi e to the power minus of z1 measure minus x upon r1 whole square upon 2 sigma 1 square, right. Similarly, PDF z2 measure will be 1 upon sigma 2 root over 2 pi e to the power minus in bracket z2 measure minus x upon r2 whole square upon 2 sigma 2 square. This is equation, these two equations combined equation 12, right. Now, we have to maximize the probability of z1 measure and z2 measure, right. Now, the likelihood function must be the probability of obtaining the measurements z1 measure and z2 measure, right. Therefore, since we are assuming that the random errors zeta 1 and zeta 2 are independent random variables, the probability of obtaining z1 measure and z2 measure is simply the product of the probability of obtaining z1 measure and the probability of obtaining z2 measure, right. That means probability of z1 measure and z2 measure is equal to probability of z1 measure into probability of z2 measure, because these two are independent, is equal to, we can write that earlier we have seen probability of z measure is equal to in general PDF z measure into dz1 measure. So, this one we can write PDF z1 measure dz1 measure into PDF z2 measure into dz2 measure, right. Or we can write PDF z1 measure into PDF z2 measure, then dz1 measure into dz2 measure, right. So, just let me reduce this volume little bit, right. No, this is okay, sorry, area. So, just hold on. So, this one, that means if you write like this, then this two we can write that if you substitute the PDF z1 measure and PDF z2 measure your what you call expressions, then you will get 1 upon sigma 1 root 2 pi e to the power minus z1 measure minus x upon r1 whole square upon 2 sigma 1 square into 1 upon sigma 2 root 2 pi e to the power minus z2 measure minus x upon r2 whole square upon 2 sigma 2 square into dz1 measure dz2 measure, that is equation 13. Actually, here also what we will do, that we got this expression, right. So, we have to maximize the probability, then ultimately what we have to do is we have to maximize the actually your what you call PDF your z1 measure into PDF z2 measure. These two we have to maximize. Again we have to take the natural logarithm of this. I told you that maximizing that PDF function here is nothing but the maximizing of the logarithm, your natural logarithm will take, and that same function, the ln function, right. So, thank you very much, we will be back again.